Hello and welcome back to Eric's YouTube channel. Today we'll be doing question 2 of the 2025 paper for complex numbers. And so, going from the first question, we're given that complex numbers u and w are represented on the Argand diagram below. And so, the way to find these coordinates is simply to find where they are by using the xy coordinate system. So x is represented on the real axes and y is represented on the imaginary axes. And so for this case, for u, we can see that it is at x4 and the y is at 2. But when we do imaginary, we have to also include I. Therefore, u is at 4 plus 2i. And for w, again, it's the same thing. X, y. So w is at -2 and y is at -3i. So right, w is -2 minus 3i. And so the question asks, given that z is equal to 2u plus 3w, we have to find z and show it on the Argand diagram above. So for the first step, we need to find what z is equal to. So z is equal to 2, and u was written up there. So write 4 plus 2i plus 3 times w, which is -2 minus 3i. Expanding out the brackets, we get 8 plus 4i minus 6 minus 9i. And simplifying that, we get 2 minus 5i. And that is our point for z. And looking back on the Argand diagram, where 2 will be our point on the real axis and y, -5 will be the point on the y-axis. So 2 and -5. So at that point will be z, 2 -5i. And that's that question done. Moving on to part B, we're given that u is equal to m cis 3 pi on 10. And we have to find u to the power of 5 in the form a plus bi. So this original expression for u is known as polar form, and a plus bi is known as rectangular form. And we have to find a way to express u in rectangular form. So what we do first is use De Moivre's theorem. So we raise this entire expression on both sides to the power of 5. This means that u to the 5 is equal, for De Moivre's theorem, it says that, in this case, it's m to the 5 cis 3 pi on this should be, this should be 10. So 10 times 5. So it's m to the 5 cis 3 pi on 2. And now we have to express this in rectangular form, and so what we can do is just go cosine 3 pi on 2 plus I sine 3 pi on 2. This gives m to the 5 cosine of 3 pi on 2, 0. And I sine 3 pi on 2 is minus I. Therefore, this simplifies just down to minus m to the 5i, which means that u to the 5 is equal to minus m to the 5i. Next question, we have to solve the following equation for m, where m is a real number. And so we see that the modulus, and from the formula sheet, the modulus of x plus iy is equivalent to the square root of x squared plus y squared, and please run brackets. So any real part is defined as x, and the imaginary part is defined as y. And so we can apply this with this question. So here 5 is the real part and minus m is the negative part. And so what we will do is do the square root. So 5 squared plus negative m squared is equal to the square root of 5m squared. Simplifying that gets us to 25 plus m squared equals square root 5m squared. Getting rid of the square root, we can square both sides. So the square root and the square cancels each other out. This gives us 25 plus m squared is equal to 5m squared. And now we need to solve for m, so we'll bring the m squared to the right hand side. So 25 is equal to 4m squared, 5, because we just bring like terms together. Dividing each side by 4 gives us that m squared is equal to 25 over 4. Now we have to find m, so we square root both sides. And the important thing is to remember when we square root that we have to consider both positive and negative. So square root, the positive square root, which means that m, simplifying that gives us that m can be plus or minus 5 on 2. Next part, we're given that this entire expression is equal to this expression on the right hand side. We have to find all possible values for g and h. So in this case, we will have to first expand out the brackets. This gives us 3g plus 3gh, just h, ghi, plus 6i plus 2hi squared, and that's equal to 30 minus 10i minus 12i plus 4i squared. And we know that square root of negative 1 is equal to I. Therefore, I squared is equal to negative 1. And using that idea, we chuck this into this expression, which gives us 3g plus ghi plus 6i minus 2h is equal to 30 minus 10i minus 12i minus 4. And if we group it by the real parts, we get 3g minus 2h plus gh plus 6i is equal to 26 minus 22i. Okay, now what we have to do is equate the real part on each side to the imaginary part on each side. So this gives us two equations, 3g minus 2h is equal to 26, and gh plus 6 is equal to negative 22. Now, in this case, we are trying to solve for g and h. And the easiest way is to first isolate and find one of these variables in terms of the other variable, and then use that and make it into quadratic or some other term. So in this case, I'll deal with the imaginary side first. And the way I got this expression is grouping that. The i's just cancel out, which gives the expression above. So here, I'm going to rearrange for g and h. So gh is equal to minus 28. And now I go h, dividing each side by g, we get minus 28 on g. Now we will substitute this into there. This gives us 3g minus 2 times minus 28 on g equal to 26. Simplifying that gives us 3g plus 56 on g is equal to 26. Now I want to multiply everything by g, which gives us 3g squared plus 56 is equal to 26g. And rearranging it to put it into quadratic form gives us 3g squared minus 26g plus 56 is 0. And now if we use our graphics calculator and put it in to solve for the values for g, we get that g is 3g minus 14 and also g minus 4. So that is it factorized, which means that g is either 14 on 3 or g is 4. And now going back to our expression for h, we have two possible values for g, and now we can use these two values to find the value of h. So using h is equal to minus 28 on g, suppose if g was equal to 14 on 3, h is equal to minus 28 on 14 on 3 because negative 6 in the other case. If g is 4, h is equal to minus 28 on 4, so h is equal to negative 7. So these will be our values for g and h respectively. Finally, we are given the argument for this expression is equal to pi and 4, and to find all possible values of d where d is a real constant. So for the first part, you need to realize that this expression here is, in the denominator is I, and we usually don't want I in the denominator, so the way to get rid of it is to do something called rationalizing the fraction. So what we do is we write the expression first. 6i minus 3i. We multiply by the conjugate, where the conjugate is the imaginary part, the coefficient, the sign flips. So in this case, it's 1 plus di. And we are allowed to do this because we're effectively multiplying by 1. Doing this gives us, in the top, we get d plus d squared I plus 6i plus 6di squared all over. You can notice here the denominator, it's essentially a difference of two squares. So to represent that, we have 1 plus di minus di minus d squared I squared. And so these two cancel out. This gives us, using the same idea, since I is equal to square root of negative 1, I squared is equal to negative 1. So using that idea in this expression, we get d plus d squared I plus 6i is plus or minus 6d all over 1 plus d squared. And grouping all real and imaginary parts together, we get minus 5d plus 6 plus d squared I all over 1 plus d squared. And now what I'd like to do is to split it, the denominator, to the real and imaginary. So this becomes minus 5d all over 1 plus d squared plus 6 plus d squared over 1 plus d squared 1 plus d squared I. So this is the rationalized expression and the one that was given in the argument. And so what we can do now, looking at the questions, is that the argument of this expression is equal to pi and 4. Now in the formula sheet, in the special triangle section, we see that the only triangle that has pi and 4 is the one listed below. This angle is pi and 4. That angle is also pi and 4. This length is 1. This length is also 1. and this length is root 2. So this means that the base length is equal to the height length. Now representing this on a graph, the argument is the distance, the angle from here. And so, this is the real axis and this is the imaginary axis. And so what this triangle shows us is that the real part of the complex number is equal to the height of the complex number. And so what this means is that the real part of d plus 6i over 1 minus di is equal to the imaginary part of d plus 6i over 1 minus di. Since we know, I'll write this below, the argument of the expression is equal to pi on 4. So using the expression over here, what we've got to do now is equate both of them and solve for d. So minus 5d on 1 plus d squared is equal to 6 plus d squared on 1 plus d squared. So if we multiply each side by 1 plus d squared, we get rid of the denominator, which gives us negative 5d is equal to 6 plus d squared. Rearranging it to put it into quadratic form, we get d squared plus 5d plus 6 is equal to 0, which means that, and factorizing this, we get d plus 2 and d plus 3 is 0, which means d is either negative 2 or d is equal to negative 3. Now for these kind of questions, you also want to make sure that your solutions result in the argument being pi on 4. So testing it by putting into this expression here, we'll call this off. So for d is equal to negative 2, we get that the expression is minus 5 minus 2 over 1 plus negative 2 squared plus 6 plus negative 2 squared over 1 plus negative 2 squared I. This gives us 10 on 5 plus 10 on 5i, which is 2 plus 2i. And also for d equals to negative 3, we have that negative 5 times negative 3 over 1 plus negative 3 squared plus 6 plus negative 3 squared all over 1 plus negative 3 squared I. This gives us 15 over 10 plus 15 10i, which is just 3 over 2 plus 3 over 2i. Then drawing these both on the Argand diagram. This is the imaginary axis and this is the real axis. So this is 2 plus 2i and 3 plus 3i is a bit less. The important part when we do arguments that are equal to pi on 4, or any argument, is to be careful of the sign. So here it's positive pi on 4, which means that both of the coordinates found must be in the first quadrant, in this one here. So both the real and the imaginary values must be positive, in which this case they are. And so both values of, so d is equal to negative 2 and d is equal to -3, and these are solutions. And so some cases you'll have where in your Argand diagram you'll have a solution here, then you also have a solution here, but this argument is not pi on 4, what this argument is. So you would accept this one but reject the solution here. That's why you should also be careful to test your values that you find. In terms of the grade, going to the start, we have finding the correct z-value and also putting it on to the Argand diagram will give you your achieved tick. Using the correct method and finding the correct value to find e equals to 5 will give you another achieved tick. Getting up to this line here, will give you your achieved tick, and finding your solution for m will give you your merit tick, and it must include plus or minus. For this next question, getting down to here's this line and this line will be your achieved tick, and getting these expressions for G and H will be your merit tick. And finally, for this excellence question, we see that getting down to this line, one of these two lines here or here, will be your achieved tick. Your merit will be establishing this, so that'll be your merit. And your excellence question will be finding your 2D values for E. And so that is the whole of question 2. Hopefully you try these questions beforehand, and this walkthrough was really helpful. Make sure to comment, like, subscribe to Eric's YouTube channel, and I'll see you next time. This is Muggy. Yeah, thank you.